Okay. So, in the last class we have started discussing about PLL and some analysis of PLL, right. So, how good it is in tracking. We have already discussed that it is very important that we track the incoming frequency and phase well, and we have seen the detrimental effect if we cannot track either the phase or frequency. Especially the frequency is very important because that gives modulation term. If you just think about the SSB-SC or any other thing. So, and of course, phase is also important because it gives attenuation if you do not track it properly. So, we have already started doing the analysis of PLL. We have already given the basic circuit diagram of a PLL, means it is a we have already told that it is probably it operates in a feedback loop with a special component that is called VCO, right, voltage control oscillator. So, whatever input voltage you gives, accordingly it will oscillate, okay, and the frequency of oscillation will be a linear, means it will have a linear response with respect to the input voltage, right. So, that is what we have done, and what we have done, the basic PLL circuit that we have given was having a multiplier followed by a loop filter, and this is the error signal that was getting generated, and then there is a feedback. In the feedback loop you have that VCO, okay. So, whatever VCO produces, that is B, let us say cos omega c t plus phi output t, okay, and the input signal which is A cos or sine, let us say omega c t plus theta I t. So, this is how we represented it. So, a sinusoidal coming, we generate a cosinusoidal signal over here from the VCO, and all we wish to do is this two phase, we want to get a proper synchronism in these two phase, input phase as well as the output phase. Okay. So, one thing we have not probably covered, that here if you see, we are already assuming that if the incoming frequency is omega c, then the phase of the frequency of the VCO also should be omega c. Let us say we have already talked about a free running frequency of VCO, let us say that is omega c, okay, or FC. So, that is already given, and my incoming frequency is not matching to that, it might be close, but it is not matching. Then what happens? Okay, will this VCO technique still operate at that point? Let us try to see that. Okay. So, let us say I have incoming signal which is a sine, instead of omega c t, that has a different frequency, let us say that is omega 0 t plus some input phase, let us say psi t is coming over. Okay. So, this is just a modified one of this one. We are just assuming over here that there is no matching in frequency. Earlier, whenever we started analyzing it, we were saying that in the analysis we will assume that the frequencies are matched, and then there is a time varying phase and we want to match that phase. Okay. So, that was our target. Now, we are saying that can we really extend that same analysis for a frequency mismatch case. Okay. So, if this is the case, I can actually rewrite this, I can write it this way, omega c t plus omega 0 minus omega c t plus psi t, no problem in doing that, right. I can always do that, and what I can do, I can actually take this part and define that as the input phase theta I t. So, I can always do that, because anyway this was not a constant thing, this was a variable of time. So, I can add another time varying part to it, and I can consider that whole thing, composite thing, as theta I t, and then what happens, immediately whatever frequency comes, I can actually represent that in terms of the free running frequency of the VCO, and then I can accordingly manipulate the input phase, okay, and the tracking will be on that phase only, right. So, I can always, the frequency mismatch, I can actually put that in phase mismatch term, and then do the analysis similarly the way we have been doing it. Okay. So, all right, after this we as we have now a good understanding that phase and frequency both we can treat similarly, what we have done, we have actually converted this particular circuit that we have shown with a multiplier, because that was actually a nonlinear circuit, to our equivalent linear circuitry, where we were treating phase as the input and phase as the VCO generated things. Okay. So, immediately we can see that it will be a linear circuit, because whenever we multiply there will be a phase plus term and phase minus term, and then there is a loop filter which is predominantly assumed to be a low pass filter. So, the plus term will be cancelled, it is just the minus term which will be there. So, if phase wise we think about that circuitry, it is just an input phase minus the output phase. So, that is a linear circuitry, right. So, that is what we have already employed. So, what we have said, we will see it from the phase perspective, not the actual signal perspective. Okay. So, immediately what happens? So, this is theta I t. So, there is theta o t which is coming in, okay, and that creates my theta e t after subtraction, okay, after the difference. Of course, because the original signal was some cos and sine. So, you multiply, there will be cos sin a plus b and sin a minus b, and a plus b terms gets cancelled. So, rest will be sin a minus b. So, if this is the phase difference, there should be a circuitry which converts it into sine, right. That should be passed through the low pass filter according to our low pass filter equation that we have derived in the previous class, right. So, that should pass through the low pass filter, and equivalently we have written that should be A k and H s, right, where H s is the transfer function of the low pass filter and A k are system defined parameter. Either it comes from the VCO or it comes from the, means it generally comes from the either signal or VCO, right. So, that is the system generated parameter. Okay. So, this should generate the error signal which we are calling as C E0 t, okay, and then that gets fed to the VCO. We have also seen, if we see it from the phase perspective, that becomes an integrator. These are the things we have already proven, right. So, it is either minus infinity to 0, or if the signal starts from 0, you can take it from 0 to t. So, either minus infinity to t. So, this is a just an integrator circuit, whereas the input is actually the output phase derivative of that, which is equal to C E0 t, right. So, that gets fed into this, because it is an integrator, it will immediately convert it to theta o t, and that gets fed over the circuit, right. So, this was the equivalent circuit that we have already means transformed. So, this circuit transformation we have already done in the previous class, right, and that was easier. Now, we want to do the analysis of this circuit, whether it is stabilizable, whether we get this error to be means in a time, if we try to see what kind of filter designing will give me this error to be 0, okay, because that is what we want. If we want a phase matching, then theta I should be equivalent to theta o. If that has to happen, then theta e must be 0, right. So, if we wish to get that, this must be 0, okay. So, phase must be matched, and then this error signal must be 0. This is what we want actually. So, that is something we wanted to achieve, right. So, if that happens, then immediately there will be a locking in the input and output phase. Okay. So, for that, as you can see, this k parameter, that was typical to the VCO, okay. It was having a parameter b, which is the actually if you just see over here, that b is the strength of the VCO output signal. So, that is typical to VCO, and then it was also having a parameter called c, which is also part of that linear variation with respect to VCO input voltage and frequency that it generates. So, this is also a parameter typical to the VCO, and k is actually half b into c, we have proven that, okay. So, that is a typical VCO related parameter, okay. So, I cannot really touch that. Once a VCO is given, I cannot touch that. A is also something which is coming along with the input signal, right. I cannot really touch that. So, what I can touch is this Hs. So, that loop filter designing has to be done properly, so that I can prove that this particular things actually track my input frequency and phase. That should be our effort now onwards, okay. So, let us try to see how do we do that. This entire circuitry, if you see, if I just convert it into S domain, this is fine, that should be integration, so it should be 1 by S, right. We know that integration equivalently in Laplace domain, that should be 1 by S, that is all fine. This is all right, typical function of S, no problem in that. Addition, no problem in that. The only problem or the nonlinearity part that is there in that sign of this signal. So, sinusoidal of something, if you wish to calculate the transfer function, that will be a nonlinear thing, right. So, the transfer function, calculation of transfer function is going to be very difficult. So, that is the only disturbing element. Now, what we will do is we will try to think that whatever happens, the incoming frequency and the corresponding phase is already very close to the one that is generated by the VCO. Okay. So, this small assumption I will take, and immediately we can say this theta E t is actually very close to 0, okay, or it is very small. I can just write that, we can write that theta E t is much less than, basically I can say pi by 2, okay. So, if I write that, so basically the error in phase is much smaller. In that case, the sinusoidal can be approximated as the angle itself. So, I can write sin theta e as almost equivalent to theta e, okay, or if it is theta e t, it must be almost equivalent to theta e t. This is something I can write, okay. Once I write that, immediately this sinusoidal goes away. So, for a small error, whenever the error is within a very small amount, I know that I can have some analysis, will characterize how much small it should be. So, all those things will be characterizing. But right now we can see that if it is, this phase error is much smaller than pi by 2, we can actually approximate the sign as the signal itself. Immediately my transfer function of this particular thing becomes very simplified. So, I have a 1 by S over here due to the integration, and I have a k h s over here, right. Fine. So, this is actually my theta I t, or in S domain I can write it as theta I s. This is actually theta O t, or I can write it as theta O s, right. So, at this point I get theta I s minus theta O s, right. This is plus, this is minus. So, basically what happens, theta I s minus theta O s, right. This if I multiply, so this is that part, if I multiply by this and this, then I get my theta O s. So, I can write theta O s is nothing but this into a k h s divided by s. That is the overall equation I can write. Immediately I get a relationship between my output phase and input phase, right. So, what is that? So, I can write theta O s, sorry, it should be theta O s, if I put it on this side, a k h s divided by s equals to theta I s into a k h s divided by s, right. So, I can write theta O s divided by theta I s is equals to a k h s divided by s plus a k h s, right. That is something I can write, fine. Okay. What is theta E s? That is equal to theta I s minus theta O s, okay. And immediately from there I can get a, also as I have got a relationship between theta O and theta I can get a relationship between theta E and theta I. So, immediately I can write this theta E s is equals to s by s plus a k h s, that is just algebraic manipulation of theta I s. If you just put that over there, I will be able to get this relationship also, right. So far it is all good. What I have to now see is, I give a input phase, and I want to see that my theta es in equivalent time domain, if I put t tends to infinity, it should go to 0. Okay. So, that should be my target, or it should go to something, wherever it goes, that is my actually phase error. Finally, I will be getting, that is the steady state phase error, because there might be oscillation and all other things, but as t tends to infinity, whatever I get, that should be the phase error I will be getting, right. So, because theta es is actually the phase error between the input and output. Okay. So, I will try to characterize that part. What do I do? Let us say my incoming signal has a frequency error. Okay. So, let us say it is A sin omega 0 t plus phi 0. Okay. So, basically what I am trying to do is, I have an input signal now which is a sinusoidal. Okay. This I might have created by squaring it and then filtering it properly. Okay. So, which we have already discussed, that double sideband suppressed carrier if we get, we actually square it, then do a filtering, whatever frequency we get, we actually make it half, then from 2 omega c we get omega c or whatever it is, that might be a little bit deviated. Okay. So, whatever we do get, we are, that is actually at, means we do not say omega c, it is omega 0, let us say. So, we get this, right. So, whatever it is, we will be getting that. Now, at the VCO generates at omega c. Okay. So, immediately I have to calculate the effective theta I t with respect to that omega c. So, I can write this as usual, or as the previous case, I can write this as omega c t plus omega 0 minus omega c t plus phi 0, right. So, that becomes my theta I t, right. So, omega c is already the free running frequency of the VCO. So, therefore, this must be my input phase. Okay. So, if this is the input phase, what is the corresponding S domain representation? Okay. So, omega 0 minus omega c t, t in S domain it is 1 by S square, right. So, it should be omega 0 minus omega c by S square. So, just go through the list of Laplace transform. So, we will be seeing that means linear in time, that gets 1 by S square, and a constant will be 1 by S, right. So, I can write that as, I do get this, right. So, theta I s is evaluated. Now, let us see theta E s from this relationship. So, immediately I can write theta E s as S by S plus A k H s into theta I s, right. So, that was what we have already written. So, theta I s I can write over here. So, that should be omega 0 minus omega c divided by S square phi 0 by S, right. So, we get this. Now, here all other things are known, the only thing that is not known is H s. So, let us try to put some H s over here. So, let us say first thing I do is a low pass filter. Okay. So, H s must be 1 within the band of interest, then it should be 0. Okay. So, I can put H s within the band of interest should be 1. Okay. So, if I just replace that, so my theta E s must be S by S plus H s becomes 1. So, it should be A k, and I do have omega 0 minus omega c divided by S square plus phi 0 by S, right. This I can write, see this should be omega 0 minus omega c divided by S into S plus A k, right, plus psi 0, S gets cancelled. So, it is S plus A k. Now, all I wish to do is theta E s I have got, I want to go to time domain representation. So, inverse Laplace transform has to be done. So, now for this I know how to evaluate inverse Laplace transform, okay, because it is in form of 1 by S plus some constant. This is still not, I can do a partial fraction evaluation and I can again represent it in this way, and it turns out to be, so omega 0 minus omega c divided by a k by s plus minus omega 0 minus omega c divided by a k divided by s plus a k, right, plus phi 0 s plus a k. This is fine. If you just add these two, you can see that things will be cancelled and you will finally get omega 0 minus omega c. Okay. So, this is a valid representation, and immediately if I just wish to do from the list of Laplace inverse transform, I can evaluate this as, see, whenever it is just 1 by s, that becomes that thing only, whatever I have. So, it should be omega 0 minus omega c divided by a k. Whenever it is s plus a k, it should have a exponential term, okay, e to the power minus that into t. So, it should be omega 0 minus omega c by a k, that should be there, and there should be a term called e to the power minus a k t. Same thing will be happening over here also. So, that should be plus phi 0 e to the power minus a k t, fine. So, I have got my phi e t representation or theta e t representation. Now, all I have to do is I have to see the final value, okay. Whenever I put time tends to infinity, that should be the steady state response of this particular circuit, right. So, for steady state response, all I have to do is I have to now put limit t tends to infinity. Immediately I can see this term will survive because that is a constant term. This, as t goes to infinity, this goes to 0. So, these two terms will be cancelled out. So, what I get is the steady state phase error, let us call that theta e at infinity, that happens to be omega 0 minus omega c by a k. So, what has happened? I have put a first order low pass filter because Hs was 1 within the band of interest, and after that it must be a low pass filter. So, whenever I put that first order characteristics or within the band all pass characteristics, what I can see that this should be the final phase error. So, there was a input frequency error, right. We have omega 0 and the free running frequency was omega c. So, it can actually track that frequency, there was no problem in that. It has tracked the frequency, whereas only there will be a phase error which is a constant phase error, which is related to these parameters, okay. Input frequency, the free running frequency, A which is the input amplitude, and K which is typical to our phase lock loop, okay, or this VCO. So, that should be the overall phase error. Fortunately, this is constant, right, constant in time. So, we will be getting a constant phase error if I just do this. What does this says for our SSB-SC modulation? It says very simple thing, that there will be a phase error, and that phase error is constant over time, constant phase error. So, that means I will be getting a attenuation in my signal. We have seen that. So, if there is a phase error in the input VCO generated output or whatever VCO generates, if there is a phase error, then there should be a amplitude degradation, or I should say attenuation. So, attenuation should be cos of this term, okay. Whatever that phase error, cos of that term only, there should be a amplitude attenuation. So, as long as we can set omega 0, omega c, means we now know how to design all this, okay, and we know how much phase shift will be there if I have that kind of loop filter, okay. So, next what we will try to do, we will try to see that by changing filter characteristics, we had a first order filter which was Hs equal to 1. If I just change the characteristics of the filter, can we really do little bit better? Can we really take the phase error also out of the picture? If this is something we can achieve, then we know that even that attenuation will not come into picture. So, in the next class we will try to evaluate that part, that if we just give some different kind of filter characteristics, can we get something better than this? Okay. So, that should be our point of discussion. Thank you.